By the end of this module, you're going to be able to do things like explain and describe the importance of data-driven decision-making, discuss methods by which data are stored and retrieved. We're going to identify different types of data, like structured versus unstructured, longitudinal versus cross-sectional, categorical versus quantitative, and observational versus experimental. We'll touch on where data comes from, different sources, and talk a little bit also about how to prepare data for analysis. Data has always been used to make business decisions, but we are swimming in more data than we ever have had before. So we're using it to make all sorts of decisions, comparing effective strategies, analyzing operations, tracking, prediction, deciphering good and bad ways to advertise to customers, or even just testing effective website designs. We're using it to make more decisions than we ever have before because we're swimming in more data than we've ever had before. I know data is important, but how much data is there really? There are probably the more obvious things that you can think of, like if you're going online making purchases, what page did you go to make those purchases? How long did you spend looking at each of those pages? Did you click any links there? And then there's also the things that are more physical, like swiping your credit card, using Apple Pay, and things of that nature. Any of those things that are recorded, whether they're values, numbers, or labels, that's what we call data. The numbers and values and labels with their context, that's data. There's a term floating around that you'll probably hear called big data. If you ask 10 different people what big data is, you're going to get 10 different answers. But more or less, big data is whenever collecting, managing, storing, or curating data becomes challenging. And that's relative. So maybe for you and your laptop, a spreadsheet that's more than 1,000 rows long becomes challenging. So for you and your laptop, that's big data. But if you're working for a company that has its own entire mainframe of supercomputers, big data means something totally different to you. Now, the more data that you have, the more that data storage becomes a problem. Where to store it, where to keep it. Now, if it's just you and you're storing data on your laptop, maybe something here on the left is more suitable for you. You're in a garage, you're in a basement, you have a little bit of a bigger computer than your laptop, you could probably store everything that you need. But if you're a larger company, you'll need more than that. You might need an entire floor dedicated in your building for just storage. So something that you might see here on the right. Wherever that data is stored, whether it's you on the left or you on the right here, we call that data warehouse or data warehouses. I know data is important, but is there really that much data out there? If you take until the beginning of time, until 2003, and you were to calculate how much data we created then, we create that much every 2 days. 90% of data in the world right now was created in the past 2 years, and the total amount of data being captured and stored just by industry alone is now doubling every year or so. And that's picking up. So next year, that's probably going to be faster. There's a documentary that was on Netflix or used to be, but if you stumble upon it, I highly recommend it. It focuses on the effects of social media on today's society, and one of the angles that it takes is that we are not used to seeing things increase as fast as computing powers increased. So from 1960 till today, computing power has increased about 1 trillion-fold exponentially. So it's not a constant increase, it's actually ramping up faster and faster and faster. We're not used to things increasing like that. We're used to things increasing like cars. Like since the beginning of cars till now, they are about twice as fast. 1 trillion is just a magnitude that we're not used to seeing in day-to-day life. To give you an example of how we're not used to seeing and working with things of that magnitude, if I was to ask you how many days are in a million seconds, pause the video, write it down on your phone or whatever you're doing right now, and just take a best guess. It's about 11 days. I think it's just a little bit more, maybe 11.2, 11.3. But then if I was to ask you how many days are in a billion seconds, you might guess something in the order of days, months, but you might be way off because it's actually 31 years. Differentiating between a million and a billion seems insignificant. They are in totally different scales. And that's million and billion. That is not even a trillion. A trillion is in its own league past these two. Every minute, there are 200 million emails sent, about 2 million Facebook likes, 250,000 tweets, 200,000 photos uploaded to Facebook, and 100 hours of YouTube videos. That's every day, 15 years worth of videos. If you wanted to sit down and digest the things that are being uploaded to YouTube, you physically couldn't. Internet users generated about 64 zettabytes in 2020. Facebook generates about 4 petabytes every day. Twitter or X uses data from tweets to measure sentiment. They do this thing called sentiment analysis where they'll analyze a sentence for things that are happy, sad, angry, or neutral and assign a sentiment to your tweet. And they do this for about 12 terabytes of tweets every day. Now, I've been throwing around words like million, billion, and trillion. And you might be wondering right now, what's a zettabyte? Well, let me put that into perspective for you. This is what our solar system looks like. In the middle is the big glowing thing called the sun. It's the thing that's in the sky every day. And around it are the 8 planets that go around it, one of which is the Earth. Now, the sun is what we call a star. In space, a star is just a clump of gas, usually hydrogen to start, that gets clumped together through gravity. And through gravity, when the gas gets really, really clumped together, the particles start colliding with each other. And through the collisions, they form heat. And through heat, things heat up and glow. And so that's what forms the star. And basically, the sun is a big hydrogen bomb, hydrogen molecules hitting each other. And the only reason it doesn't explode like a hydrogen bomb is the gravity pulling things back in towards itself. Now, these two photos are pictures of galaxies. They're actually pictures of what we think our galaxy looks like. We don't know because if you can imagine, you were sitting inside of a pizza and someone asked you what the pizza looks like. It's impossible to know. You're in it. So this is our best guess of what our galaxy looks like. Basically, a galaxy is a collection of suns or a collection of stars. On the left, I've pointed out where our sun is, and there's somewhere between 100 billion and 400 billion stars in our galaxy alone. And you know what billion means now, so you can really appreciate that there's a lot of stars in our galaxy. Now, this picture is called the Hubble Ultra Deep Field. It was taken between 2003 and 2004 by pointing the Hubble telescope at a spot in the sky and letting it sit there for a while to let the light come and hit the lens. The light was traveling from stars from ages and ages away, so it can take quite a long time to see the light from these stars to get a picture of what's out there. Now, every spot in this picture is not a single star. It's an entire galaxy, similar to ours. Some are bigger, some are smaller. They're not all created equal. So it's possible that every dot here is a collection of 100 billion to 400 billion stars. Could be more, could be less. In this picture alone, it's estimated that there are 10,000 galaxies. And you might be wondering, that's a lot of galaxies. Every one of them could have somewhere between 100 billion to 400 billion stars. You're doing the quick math. That's a lot of stars in the sky. This is not the entire sky. This is the equivalent if you were to take a straw, hold it up to the sky, and look through it. This is only 1/10,000,000th of the sky. So taking that into account, how many stars do you think are in the universe? NASA's best estimates are that there's somewhere around 10 to the 21 stars in the universe. That is 10 followed by 21 zeros. That is 1 zettabyte. In 2020, internet users created that amount of data 64 times over. So when I say that there is a lot of data out there, this was my best attempt at putting how much data is out there in perspective, and I probably am still not doing it quite justice. Now, the chief economist at Google, or at least used to be, was Hal Varian, and Hal is on the record when Google was still getting its feet under itself, saying that statistician was going to be the sexiest job moving forward in the next 30 years. Now, Hal said that because Hal understood how Google used statisticians, and that combining them with data could do some pretty powerful things. At the time, people snickered and laughed because, they're the number nerds. What else are they good for? But over the next 30 years, computer scientists, data scientists started becoming the next hot thing. And Harvard Business Review came out and said the data scientist is going to be the sexiest job of the 21st century because already General Electric had been using them to optimize their service contracts. Google had grown to be what Google is now through statisticians and their use of data. And even Netflix developed this contest called The Prize, where they were going to give any science team $1 million if they could make the best recommendation system. And the team that won used stats. They used the root mean squared error, which is a general measure to tell how good a line of best fit is fitting to a bunch of data points. Now, before we get into data analysis and what that all entails, there are going to be phrases and words that you hear repeatedly. Things like data mining, predictive analytics, and business analytics, for example. So when those words pop up, I'm going to do my best to bold them, underline them, show them in blue, so you know what they are, so you can kind of make a note of like, I'm going to want to know what this thing is. I'm about to hear it a lot or down the road. Things like data mining, obtaining actionable information from data. Things like predictive analytics, using data to predict future things, such as performance. Or business analytics, pretty much using data to answer a business question or to inform a business decision. Now, data is the numbers and labels that we record, but all data also comes with context, and that context is just as important or sometimes more important than the numbers and labels themselves. Things like, what do the values and labels represent, where do they come from, and how they were collected. The answers to these questions usually determine how useful the data is, how we can use the data, or even what kind of questions can we answer. Now, more often than not, in this class at least, the way we'll view data is in what I call a data table. That's a picture of one right down here, and basically it's a collection of rows and columns where all the names and labels are stored. Basically, any data table should tell you things like the who and the what when it comes to things like context. Now, when it comes to this data table, I want you to look at the rows first. Sometimes we call the rows cases, but regardless, the rows tell you the who. In this row, you can see under name it says Monique, so this entire row is dedicated to Monique. The row above, that name is Chris. This row corresponds to Chris. Now, the columns, like I called out name, are called variables. So the different variables here are order number, name, state, country, price, area code, album download, gift, stock ID, and artist. They tell you the what. The what about the who is being measured or recorded. So going back to Chris's row, those other variables, order number, state, country, price, and area code, those are for Chris G in that row. So Chris G, Massachusetts, 999, 413, those are all for Chris. So the rows are called cases and they tell you the who, and the columns are called variables and they tell you the what is being measured or recorded about the who. Now I mentioned the context is as important or even more important than the numbers and labels themselves. So what particularly about context makes it so important? You can imagine if I asked people in Ohio, how did they feel about the previous election? The answers I get could greatly depend on who I ask. So if I was to ask the entire state of Ohio, that is everybody, so the picture on the left, how I have the entire state of Ohio shaded green, that might be way different than if I was to just ask the people in Oxford, the picture in the center where I just have Oxford highlighted in green. But those two could dramatically differ in answers as if I were to ask all of the metro areas in Ohio, the picture on the right where I've got Cincinnati, Dayton, Columbus, Toledo, and Cleveland highlighted. So where data is collected can massively drive the kind of responses you get and the kind of questions you can answer. But this idea of where data is collected extends further than just states. Yes, you can think of the difference in cities of if I ask people in Oxford versus Cincinnati, or if I ask people in California versus South Dakota, or if I ask people in Mexico versus Switzerland. Asking people from those areas the same question might garner very different responses, meaning where data is collected plays a really big role. How the data is collected can also make a huge difference in the kind of responses that you get. It can be the difference between having data that is very insightful versus data that doesn't really tell you anything useful. It can also be the difference between being able to make powerful predictions versus having some misleading conclusions at your hands. Going back to that same question, how does Ohio feel about the previous elections? Depending on how you collect that data, you can land yourself in these same scenarios. There was a group from Michigan State called Teachers in Social Media, and their sole purpose was to determine the relationship between social media and how students learn math in K-12 classrooms. And the way they did that is they looked at teachers who would share their teaching materials on social media platforms like Pinterest. And teachers on Pinterest didn't just share their teaching materials, but they shared things like the way their rooms were set up, what kind of posters and things were on the wall, what kind of things did they do throughout the day with their students, activities. It wasn't just assignments and exams. Now, they were also privy to some of the state scores for these schools and students. So not only could they see what the different teachers were doing in different classrooms across the US, but they could see how their students were doing, which would make a very interesting analysis question of, if you have students sitting in a circle versus in rows, or you've got pictures of such and such on the wall versus other pictures, or you're giving these kind of exams versus other kind of exams, which students performed better. Now, they're from Michigan State, so you wouldn't be able to just look at schools in Michigan and make some kind of conclusion for all of the students in the country. You'd probably want to grab students in other states as well. You'd probably want to grab some students in every state. But you probably also want to make sure you get some students in rural areas versus some students in more urban areas. Basically, you would want to make sure that the students and schools that you analyzed were what we would like to call are representative of the country. That is, if you can look at a smaller section of schools to make an accurate claim about most of the other schools. And that was actually the hardest question of the entire project. It was not how to run the analysis of what kind of things do better in terms of student performance. It's which schools, in which areas, and which students should we examine to make the most accurate claim for the entire country. And just answering that part took millions and millions of dollars and multiple years just to get a list of schools in which counties, in which districts, in which states that you should analyze if you wanted to make correct conclusions about the country. Sometimes when you collect data in a current year versus data a decade ago, that data means totally different things. I worked on a project where we predicted baseball game outcomes, and the hardest part was not making those predictions. It was, what kind of data should we use to make those predictions? Many of you familiar with baseball know that the people on a baseball team change, sometimes slowly, sometimes dramatically, from year to year, from month to month, or maybe it takes 3 or 4 years. So if you want to even just predict how the Reds are going to do this year game to game, you might think to use last year's data, maybe 2 years ago, but if those players are different, it might not make sense to use that data at all. So how long ago can you collect data and it still be applicable today can be a very challenging and important question to answer before you even get to the analysis. So I want to talk about the different types of data that we're going to work with in this course. There are many more than these two types, but quite often we use these two bins to separate the different types that you'll see most often. The first type is called categorical or qualitative. This is data that consists of names, labels, or symbolic representations for categories. Now, I named that last one real specifically, and I'll tell you here in a few slides why. But here on the right, here are some questions that would result in qualitative data. How do you feel about Miami on a scale of 1 to 5? What class of student are you? Freshman, sophomore, junior, or senior? Do you click on ads while using your phone? Yes or no? Do you invest in the stock market? Yes or no? The answers to these questions are names, labels, or symbolic representations for categories. So if you were to look at a JUMP data set, this is one that we'll work through with this in this class, that is called accidental drug deaths. And the variables here are ID, age in years, sex, race, and location. These last 3 variables, sex, race, and location, are qualitative because the answers to these are names, labels, or symbolic representations. These literally being labels, so male, female, black, white, Hispanic, hospital, residence, other. The other primary type of data that we're going to work with in this semester is called quantitative data. And here I say with a small asterisk, numerical, and I'll say here why in a second, that this is data that's measured with numerical values and units, the units playing a critical role. They tell you how each value has been measured, what the corresponding scale is, how much of something of a case has, and how far apart 2 values are. So the answers to these 4 questions here on the left would result in quantitative data. How many cups of coffee do you drink in a week? How many hours per week do you study? How many apps do you have on your phone? And how much have you invested in stocks this year? So in that same data set I just showed you, the accidental drug deaths, the variable age here is quantitative because it was measured in years. which is numerical. So 48, 30, 23, 23, 21. Yes, they are numbers, but they have a unit, and the unit is years. Both of those things are prerequisites for being quantitative data or having a quantitative variable. Now, numbers are not necessarily quantitative. We use numbers for things that are not quantitative all the time. A great example is that very first column in that data set, ID. Those are numbers, but there are no units, and we wouldn't consider that variable quantitative. Why? Things like social security number, phone numbers, and addresses do use numbers, but they don't use them in a quantitative sense. They use them in a categorical, symbolic representation sense. That is, we can't do math operations on those numbers. If I take your social security number and I add it to my social security number, you will not get another social security number that makes sense. Same thing with our phone numbers and our addresses. If my phone number starts with a 6 and yours starts with a 3, it doesn't make sense to say that mine is twice as big as yours is. So to determine whether things are quantitative or qualitative when numbers are at play, the first question to ask is, do basic math operations make sense? Things like addition, adding two bank account accounts, subtracting a person's weight by another weight, adding two social security numbers together. If these make sense, then you probably have something quantitative on your hands. If it doesn't make sense to do things like addition, you probably have something qualitative on your hands. If this doesn't quite clear it up, then you might have to ask yourself quite literally, are the numbers here symbolic or are they meaningful in a math sense? There will be times when it'll be very clear cut which type of variable you have, whether you have something that's qualitative, so labels and names, or quantitative, numbers with units. But sometimes a variable can be one or the other depending on how it's measured. Age is a very good example. If you take somebody's age and you measure it in years, then you can do things like finding the average age, finding the median age, maximum age, minimum age. But if you take age as a category and measure it as, is somebody a child, teen, adult, or senior, then performing any math operations is no longer possible. So you can't find things like the average age. Now, depending on what the question in the hand is, it might make sense to measure it in something like years, or it might make sense to measure it in something like categories like children, teen, adults, or seniors. Now, that very first variable in the accidental drug death data set was called ID, and that's a different type of variable that's not qualitative or quantitative. We call them identifier variables. Sometimes they can be letters or numbers or a mixture of both, but they are unique values that are assigned to each case, so each row, for the use of identification. Sometimes it's just for convenience, so something like a tracking number or a transaction number, and other times it's used for identification for keeping things anonymous, like student ID numbers. Now, under the qualitative data type, there are a few subtypes that we'll encounter. One type are the ones that don't really have any natural order to them, things like blood type or eye color. We'll call those nominal. There are others that will have a natural order, things like coarse grades, and we call those ordinal. The reason that we want to make a distinction is that the way we analyze these two is a little bit different. So order, ordinal, no order, nominal. When we collect data all at one point in time, we call that cross-sectional. And that can be any type of data. It could be quantitative or qualitative, but it's measured at one point in time. It could be like sales data, revenue, number of customers, expenses, and the point in time could be over the span of 1 month, it could be 1 day, it could be 1 year, but there is one measurement being taken. Now, some of the most interesting questions are answered collecting data over time, multiple time points. And that data is either known as time series or longitudinal. And kind of like cross-sectional, that the points in time could be months, they could be years, days, minutes, seconds even. But you're measuring multiple time points. So maybe you're gonna take somebody's heart rate every 30 seconds and you're gonna do it 5 times. Or we're going to look at the revenue for a company every month and we're gonna do it for 5 years. Since the type of data that we have at hand determines what kind of things we can do with it and what kind of questions we can answer, it's usually useful to have a master list of all of the variables that we have at hand, the types of variables they are, and if they're quantitative, what are the units. We call this list metadata. And so this is a little table of an example of what metadata might look like. It says, hey, we've got some data. It has account ID, pre-spending, post-spending, age, segment, enrollment, offer, and segment spending. And it says which ones are quantitative, and if so, the units. And it says which ones are categorical, and if so, are they nominal or ordinal. It also mentions at the end that this data is cross-sectional, so we can expect that these measurements, whatever the time frame was, were only taken once. Now, when it comes to sources of data, we're really not going to talk as much about, whether you got it from Twitter or Instagram, or you went to the library, or where it came from. We're going to talk about how it was collected. So the very first source I want to talk about is called experimental data. Now, when you hear the word experiment, you might think of what's in this picture right here. You got a few people, they've got the lab coats on, they've got the glasses, they're pouring stuff into beakers, and something cool is happening and they're pretty psyched about it. But that's not what makes it an experiment. What makes this an experiment is that what's happening in the beaker wouldn't happen without whatever they are doing. So when I say that experiment is actively controlling variables, it's that you are playing an active role in what the data is or what's happening with the data. Before they poured whatever they poured into this beaker, it may not have been blue, it may not have been exploding. And solely because they did what they did, it now has turned blue and is now exploding everywhere. Now, the reason experimental data can be very good, quote unquote, is that when done right, it allows us to answer very specific questions. If you want to know what kind of food plays well with your body or what kind of things upset your stomach, you could perform an experiment. You could actively control which foods you eat and carefully select, well, I'm going to try one food at a time. And I try one, everything's fine. So then I'll stop eating that and I'll try another. And then that one's fine. And then I'll stop that and I'll try a third. And if the third upsets your stomach, it's reasonable to say that it was probably that third food that did. So it's you controlling variables and being able to answer a very specific question because you control that variable. And if you're wondering, well, why don't we do experiments all the time? One, we do experiments quite often because they produce quite good data, but experiments are often very expensive to do. They are often very difficult to get right. And even if you can do both of those things, sometimes they can be immoral or even illegal. A really good example of this is retention of students in K through 12. So say you're in the third grade, but by the end of the year, you don't perform up to third grade standards. So in some states, they will hold you back, quote unquote, to redo the third grade. In other states, they will not hold you back. You will go on to the fourth grade. If you're held back, that's called being retained. If you go on to the fourth grade, it's called not being retained. Now, we've been analyzing data from retained students and not retained students for almost 50 to 60 years now. And as a country, we still don't know which is better to do in terms of student performance. Is it better to hold students back to redo the grade, or is it better to put them forward? Some states believe that it's better to hold them back because if you didn't perform up to standards, it's likely that you didn't learn the requisite material. So it doesn't make sense to go on if you don't know the material you're going to need moving forward. Other states believe that it's not that simple and that what goes into your knowledge base is not just what you learn, but it's who you're around with. So if you hold a student back, it may be better for their performance, but it may be worse for their interactions with their peers and how they grow up as a whole. So looking at a more holistic picture, it's not clear cut which is better. If one wanted to know for sure which was better, you should perform an experiment. You would have to take students probably from across every state so you can be sure that your results are applicable to every state, and you'd have to get some students who were retained and some who are not. But to make it a fair comparison, you would want to make sure that you randomly selected some students to be retained and some to not be retained. So you make sure that you start out on even footing for both groups. The problem is that it's not really immoral, and it is also illegal, to hold students back randomly. You know, if Sally and Jim have a daughter and their daughter did great in 3rd grade, it is illegal to tell them, you know what, we know Sally did really well, but Sally's part of this experiment and she was randomly selected to be held back. We are so sorry. Since we can't adequately perform this experiment, we don't know to this day which is a better course of action. Some states believe that it's better to retain students, so they do, and some states believe it's better to not retain students, so they don't. The other type of data source that I want to talk about is observational data, data that you collect by simply being an observer, and that data would occur whether you are collecting it or not. Most of the data on the internet falls under this category. That is, the things that are being recorded are through peer observation with no control, and that data, those observations would occur regardless if they were being recorded or not. So anything recorded on Twitter or Instagram or Facebook would be purely observational data. Now, there are pros and cons to this type of data as well. This data is typically very easy and inexpensive to collect. It's usually just a matter of time. The bad part is that since there is no controlling going on and you get to choose what you observe and what you don't, it can be very hard to make any definitive conclusions from the data you collect. Or worse, you might have spurious results coming from your data, so they might tell you some misleading conclusions. Spurious results are when 2 or more variables seem to cause one another, but the relationship is either purely coincidental or caused by another variable that you didn't observe. Just because you picked 2 variables to observe online and you put them on a graph and they seem to have a pattern between the two doesn't mean one causes the other. There are plenty of examples of these, and I've got a few to show you now. Here is a graph that compares the number of people who've drowned by falling into a pool over the years, along with the films Nicolas Cage has appeared in. And as you can see, they actually track quite closely. When one goes up, the other one goes up. When one goes down, the other one goes down. But this relationship is purely coincidental. Nick Cage appearing in a film is not causing more or less people to drown in a pool. Another silly example is looking at the points scored by losing teams in the Super Bowl over the years and comparing it to the number of people killed by venomous spiders. Again, pattern seems to track. When one goes up, the other one goes up. When one goes down, the other one goes down. But these are not causing one another. If a team in the Super Bowl loses by a lot of points, it doesn't mean more people are going to die by venomous spiders. Now you might look at these two and go, yes, of course, I can tell the difference between those two. Of course, those variables don't cause one another. That's not the hard part. The hard part is when you have 2 variables that look like they could cause each other. And there is a relationship when you look at the graph to tell if there is actually causation going on or not. Here are 2 very good examples. Here is a scatter plot of 40 countries, and one variable is the doctors per person, and the other variable is the life expectancy. Now again, seems like there is a pattern here, as when one goes up, the other one goes up. But these 2 variables seem to make sense. More doctors per person in a country could mean that causes them to live longer, because doctors and health kind of go together, or at least it makes sense they would go together. But what if I told you that we also looked at the number of TVs per person? So if you were to look at the TVs per person and their life expectancy, you would see a very similar pattern. When one goes up, the other one goes up. The difference here is usually that people don't think TVs per person and life expectancy go together at all. Why would more TVs per person cause people to live longer? But if you were to look at these 2 graphs side by side, other than your own internal intuition, there is nothing to distinguish these 2 graphs from each other. They both show a very similar, almost identical pattern. But we don't want to rely on our inner intuition for many reasons. One, it can be very misled, it can be biased, so we want to avoid that at all costs.
All right, that's it as far as what data is, how much data is there, and why you should care. In the next video, we'll talk about how to analyze and describe qualitative data.